Okay, so it should be recording now.
Yeah. Yes.
Okay, so welcome everybody to round 2 of the Algebra, Particles, and Quantum Theory seminar series. I'm pleased to introduce you to tonight's speaker, Lev Vaidman. Lev is a professor of physics and head of a quantum group at Tel Aviv University. He received his PhD there under the guidance of Yakir Aharonov, with whom he still collaborates. He later held a faculty position at the University of South Carolina before finally returning to Tel Aviv. Professor Vaidman is a leading expert in quantum foundations and has made significant contributions to quantum information theory. He's well known for introducing teleportation of continuous variables, cryptography with orthogonal states, novel types of quantum measurement that is non-local, weak, protective, interaction-free, and for introducing numerous quantum paradoxes. Together with Avshalom Elitzur, he invented what is known as Elitzur-Vaidman bomb tester. This is a thought experiment that allows one to check whether or not a bomb is present without necessarily detonating it. Tonight, Lev will tell us unapologetically why the many worlds interpretation is the best interpretation. He will also describe for us the current status on how probabilities are assigned in this deterministic theory. Now, before we begin, I would like to emphasize that everybody who showed up here today is here to learn. And so I hope that everyone feels comfortable enough to raise their hand and ask a question throughout the talk if they have one. If you accidentally ask a silly question, it is not a big deal. You just brush yourself off and try again next time. I would especially like to encourage questions from graduate students, upper level undergraduates, and postdocs. So Lev, anytime you're ready.
Thank you, Nicole.
My pleasure.
And you know, I don't remember how I saw this series of lectures. There were some lectures on foundations, but usually when I hear algebra and in connection to interpretation of quantum mechanics, I stop listening. So for me, it's very algebra is something very foreign. It's not that I think you don't need algebra, but algebra is not for interpretation of quantum mechanics. It's just maybe for building quantum mechanics. And particles. I believe everything waves. There are no particles. There is only wave of particles. So I thank you again for bringing me here. Maybe I will make some other people think this way. At least I hope. Okay. So, you know, Google tell me that the purpose of science is to explain and understand. And it's supposed to explain how the nature works. And really what I want to explain is my experience. Maybe there are other things in nature which we don't feel, I don't care. And but again, it's not that I want just to understand experience. I want to understand why I have this experience. So I do believe that there is some ontology behind it. And so I want to see how my experience supervenes this ontology of the world around us. And my experience, just my memories, my records. It's not when I go and perform my experiments, this is my experience. And scientific theory, from my experience and others, is supposed to connect these records of preparation with records of outcomes. In my memories, there are all kinds of situations which I can consider experiments, and they have some results. And I want my theory is supposed to give this connection. And there are, from observation, I know that there are two kinds of connections. Sometimes the connection is really definite. So the time of some object falling down is the same up to precision I can measure. And sometimes it looks like things are random. And but even if things are random, I prepare the same situation, and I see that there is some frequency of outcomes. So I expect that first my theory will tell me why I have definite predictions of some experiments with definite outcomes, and also it will tell me something about this frequency of results when they happen to be random. Now, I believe that many-word interpretation is the only deterministic theory without action at a distance, which makes this connection. And these two things, I think, are very important for me. So I will start explaining what I believe is a good physics explanation. Classical explanation is good because it's local and deterministic, but it's wrong. So I will go to quantum explanation in simple, hypothetical case. In fact, we don't have it. When we don't when we don't have any experiment with random outcome, somehow we prevent randomness. We only perform experiments, the outcomes of which are definite. And then, in fact, I will perform the experiment. In my homepage, there is a word splitter. So I will perform the experiment. I split the word. This is a quantum experiment. And I will do it for a purpose. I don't have too much time, and I want to explain why I believe, or why I prefer many-word interpretation to others. And once I wrote a paper discussing two experiments, one which I was involved, one interaction-free measurement and one teleportation. So both of them lead me to many words. So I will perform splitting of the word in two different words. In one of them, I will talk about interaction-free measurement, and in another one, I will talk about teleportation. So it will be something like this. So I really believe this will happen. At the same time, I will talk about teleportation and about interaction-free measurement. But this will be in different words, so it will be, both of them will exist, but one in one word, another in another. I will continue with brief description what the many-word is for me. And then I will go to some maybe more difficult issues. We'll see. If there will be no much time, then my main purpose is really to persuade you that many-word is good. Probability in many-word, it's difficult. So I will try to explain what is the problem with probability. And the Born rule, this is part of quantum theory. And this is kind of a technical thing, which also, if there will be no time, I might skip it. I will present the proof of Born rule. It's not necessarily in many-word framework, just in quantum mechanics. And then I will talk more about how to understand probability in many words. And I will end up with conclusions. Okay, what is good explanation? I believe that determinism is part of the good explanation, and I have some references. Nothing occurs at random, but everything for reason and by necessity. This was very long ago. And then Laplace famously was telling us that an intellect which at a certain moment would know all forces that set nature in motion and all position of all items of which nature is composed, if this intellect were also vast enough to submit this data to analysis, it would embrace in a single formula the movement of the greatest bodies of the universe and those of the tiniest atoms. For such an intellect, nothing would be uncertain, and the future, just like the past, would be present before its eyes. Now, this was kind of relatively still long ago, but today philosophers, at least they admit the following. Ehrman, I think, is one leading philosopher about determinism, and he writes, only after long and repeated failure may we entertain the hypothesis that the failure to find deterministic law does not represent a lack of imagination or diligence on our part, but reflects the fact that the nature is non-deterministic. If I understand correctly, he really says that we failed to have deterministic picture. And in fact, he blamed quantum mechanics. But I believe that it's not necessarily so. Okay, so another aspect of good explanation for me, it's a local action. In fact, my teacher, Aronov, has this Aronov boom effect, which is also kind of non-local. And recently, I also say that there is a local explanation for Aronov boom effect. But okay, this kind of, I believe things, if something, I want to change the motion of something, I have to touch it and push it. And again, I have some good people to support this view. In fact, one of them created a theory which is non-local, it's Newton. But after creating this theory, he says it's inconceivable that inanimate matter affects other matter without mutual contact. No man who has in philosophical matter a competent faculty of thinking can ever fall into it. So his gravitational force was kind of immediate. If I'll move my hand here, according to Newton's law, the attraction of moon during gravity of my hand will change immediately. And he didn't know how to resolve it, but he saw the difficulty. And I have, of course, Einstein to support me. Principle of local action. If A and B are spatially distant things, then external influence on A has no immediate effect on B. So I believe the good explanation is local explanation. If something moves or changes its motion, I have to come and push it. And no problem with gravity, because I don't know exactly history of physics when the idea of field come out, but Earth creates gravitational fields. It's come to the place where there are other objects, and this other object locally feels this field. And there is this force, local force, and then they get accelerated because of local action. Okay, so classical physics is great. We have particles, according to Newton, which have trajectories, and they change their velocity according to acceleration because the local force is acting on them. It's local in 3 dimensions, it's deterministic, and sometimes we have probabilistic experiments, but they all explained by ignorance about details of preparation. So if we send a kind of big ball on a plate or tennis ball, then it's reflected, and we know always this will happen this way. But if we have something very small and this surface has some holes, sometimes it can go and sometimes it can reflect. But again, we understand the reason, because we don't see exactly, we cannot point exactly our ball, and sometimes it goes reflected and sometimes it goes through a hole. So, and classical physics was very successful, but it's failed to it's in many things. So, and it's explained big object and small object by the same physics, but it failed. We had famously black body radiation, hydrogen atom, which cannot be stable. But for me, I like interferometer. Granger and Aspect made interferometer, Mach-Zehnder interferometer with single particles, and they saw that even single particles, you can get constructive interference in one place and destructive in another place. And if we think about photons as particles, we cannot find explanation. We cannot explain classically why always when we hit this, we test before. Sometimes this surface make particle through, sometimes reflect. But in this case, it's always go here. So classical physics cannot explain it. Quantum physics can. What quantum physics tell us is particles are waves. And if particles are waves, then Mach-Zehnder interferometer was understood as wave phenomena more than 100 years ago. So we just photons is a wave, it's go, it splits, and then it destructively interfere in one place and constructively interfere in another place. And so we have a nice explanation of tuned Mach-Zehnder interferometer. And in fact, we can great explanation almost of everything else. Everything which we can calculate and everything which we can measure. There is agreement between experiment and the theory. Sometimes our theory is not precise and we don't know exactly, sometimes experiment. But in every place where we can calculate and measure, essentially, there is no discrepancy. It's explained everything. However, it's explained everything only if we do not perform this measurement, which kind of with quantum measurement. It's explained that it makes deterministic predictions. So if we do not live in Soviet Union or Russia, whatever, so I don't think we can forbid quantum experiment. But if in some world all quantum experiments will be forbidden, no one will be able to build single photon detectors or any kind of devices, then I think quantum experiment will explain everything. So in this world, everything is explained. There is this famous cartoon, but I think it was kind of wrong. They say that when you go from quantum to classical, we should worry about classical apparatus. What I worry, it's about quantum apparatus, like Geiger counter or this kind of things. This is you are not supposed to build. If you don't build, then we will not have Shenker cats. We will have only well-defined classical world. This will be a single quantum world, which is essentially like classical. So the world which I'm talking, it's a universe which happen to have only one word. It's multiverse in maybe in Deutsch language. In this universe, all macroscopic objects are really in the product state. They're all well localized. They're not entangled. And so everything is just have one classical nice description. We can look on tiger, look on the part of his body, and everything in all macroscopic parts product state. And we can still, of course, there are particles and we have to explain stability of atoms and everything. Then we have to understand that there is entanglement and not everything is a product state. But all macroscopic things are in a product state. So if we do not perform experiment which can create superposition of macroscopic bodies, when we have everything in this nice way. And I said against algebra, it's some operators. I think in principle we can make direct connection between the wave function and objects. If there is a wave function in the shape of a tiger, then it's a tiger. I don't need any operators to define tiger. Just density of particles, whatever will have a shape of tiger, this is a tiger. Okay, but this experiment we are not supposed to do. Because quantum mechanics tell us that it has equations and the wave change description of two detectors. If detectors are photomultipliers, we can in fact see what's exactly happening. And our equations tell us that it should happen in both. And so in fact we see one, and in fact the theory tells us one. We just don't want to believe that we see one. So this is kind of forbidden experiment, and let's perform this kind of experiment. Let's go to my homepage, But before, I will, as I said, I want to perform this experiment for a purpose. And long time ago, I wrote this paper on paradoxical aspect of new quantum experiment. And this was also motivation why, another reason why we should believe in many world interpretation. One of these because this was interaction-free measurement, and another one is teleportation. Both are experiment, I think, paradoxical if you believe in one word. So I will explain its paradoxality in one of them, but which one? In fact, both of them, but in parallel words. So for this, I need to split the word. And everyone, can, if somebody has iPhones, you can use, there is a $2 application, but you can go for free to my homepage. There is a word splitter. And then you go here, you can split from 2 to up to 6, but then we need 2. So I go here, you click here, and then I say, let's say, teleportation. And here I say IFM, interaction-free measurement. So and then I say, now, when I touch split, then it will connect to quantum experiment. And this quantum experiment will split the words. And we will get, one of me will get IFM, another one will get teleportation. And I really believe that the other exist. So let's do the experiment.
So this is, I don't know if it's supposed to be displaying on the screen, but we can't see it.
Ah, you can't see it?
No.
Oh, too bad. Because yes, now I understand why you cannot see it. Okay. Sorry, you had to tell me before, but just sorry.
Yeah, no worries.
Let me stop share and then share screen. Let's do it again. Share. Now you see something, correct?
Yes, so it says instructions and it's got dice.
Okay, so now perfect. How I came to this, in my homepage, there is a link to a word splitter. When you click, then you get to this page, and this is a word splitter. And so maybe it will now be not teleportation because I will do it again. So I want to split again. I go here, so it gives me again 2 options, and I will write again teleportation, and here I will write IFM. And now in the moment I click on split, the experiment will be performed again. So let's split it. Oh, now it's IFM. So in this word, I will discuss IFM, maybe in a word in which, classical word in which I would make the sharing to the whole, not to the PowerPoint. It would be teleport anyway. So IFM. Let's close this. Hope. So I hope you still see it. You're supposed to see it. So, and then interaction-free measurement happened immediately after. So the story was that just a few months ago, there was a conference in Chapman, 30 years of interaction, Lev Vaidman interaction-free measurement. Avi Elitzur, in fact, 33 years ago, it took like 3 years to publish, asked me the following question. Let's suppose we have a super sensitive detector or bomb. You're not supposed to touch it. Not supposed to shed light on it, because it's whatever photon any quantum particle reaches, it explodes. So, and this is the only interaction with the world it makes, only through the explosion. So this is what it's the only thing, if you touch it. And then he asked, can this object be found without explosion? Of course, you can fund it by, and then it will explode. But the question, is it possible to find such an object without explosion? And in fact, the solution is extremely simple. It's not clear why no one asked this question before. Because the fact that it's possible, it's really very paradoxical if we think in classical terms. And the solution is just tuned Mach-Zehnder interferometer. If we send a single particle Mach-Zehnder interferometer and it's tuned in such a way that it cannot, that we have a dark port, and we tune it and then we arrange it in such a way that one of the arms goes through the place where it might be a bomb. All other place which we test and we know that nothing is there. So now, if the bomb is there and we send it, then first, yeah, it might explode. This is not good. But there is a chance that it will not explode. You see, there is a photon in two places, and it might happen that it will not explode. If it will not explode, then the photon will continue here. And then it has a chance to come here, 25%, but there is a chance. If this happens, then there is a paradoxical story. We know that there is a bomb. This is a bomb which we are not supposed to, the only interaction of the bomb with nature is by explosion. But it's not exploded. We cannot find photon both here and here. And we know we didn't touch it, first because it didn't explode. But from my point of view, there is more reason for it. I know that there is no trace of whatsoever of the photon near the bomb. So I believe we really didn't touch the bomb. So for me, this is paradox and not acceptable. If there is only one word, this place may be far away in some, nothing was there, no light was there, nothing. And then we arrange this interferometer and we make the experiment. And now we get information about some place that no particle was there, no particle sent anything from there. For me, the whole science supposed to talk, it's about causality. And these things are causal. So this cannot be true. So this paradox. Now, many words resolve this paradox. How it resolves this paradox? Because many words tell us physics, it's not just for our words. Physics is for all words together. It's true that in our world, we get this click and we know that there is a bomb. But in nature, that was another word with explosion. The photon was there. So there is no, this is not nature. Again, our intuition comes from physics, which describe all the words. If you look on all the words together, the photon was there. So it's not so strange. It's a clever device that in our world will know something useful, and the payment is the prices that in parallel worlds there is explosion. In fact, essentially quantum computer works in a similar way. We kind of we arranged that in our world we know what we want to know, but it was made in, making calculation in many parallel worlds. Okay. So this is my motivation for many words, but let us now explain what it is. Let's briefly go through teleportation because this is, I will not have time both for this. Okay. So from physics point of view, the many words tells that there is the only ontology, and there is ontology. It's not something, I do have ontology. Ontology, it's the wave function of the universe, a large entangled wave function of the universe. It's not exactly Schrödinger equation. I know it's wrong. It's not relativistic, but some generalization of Schrödinger equation, relativistic generalization of Schrödinger equation. And this is the only ontology. There is nothing else. And the difference from textbook quantum mechanics that it doesn't collapse at measurements. So maybe this is kind of pictorial situation. Every splitting is kind of measurement of different classical stories. And ontology is just psi, which evolves deterministically because the Schrödinger equation is deterministic equation. there are multiple words similar to the one we experience. This big universal wave function can be decomposed. It's not exactly precise way. There is we can play with it. What is word? Word for me is defined that all macroscopic objects are well localized. But what's macroscopic? It's what's well localized. One can decide according to his taste, according to the devices he has. Now, in a word, by definition, if all macroscopic objects are well localized, they all in the product state with the rest. So we have product states. If I look on center of mass, of position, or direction of all macroscopic objects, they're all in product states and they're all in 3 dimensions. Sometimes Dave Albert says that the physics is in configuration space. We need configuration space to explain this, but to explain what we see around, we need 3 dimensions, and all macroscopic objects, the wave function of macroscopic objects, live in 3 dimensions. And again, word is not defined. Here I wrote some mathematical story, but word is defined by us, by the conscious being, to help to explain our experience. Because ontology is this big universal wave function, highly entangled, and which we are aware of only a small part of it. And the word is our concept, which help us to divide this universal wave function to wave function of words. Now, each wave function of word includes all space. Sometimes even proponents of many words say it's propagate with the speed of light. No, every wave function of the word, it's everywhere. Now, so universe, entangled wave function evolving deterministic without actually the distance. But again, it can be viewed as superposition of this word wave function, or superposition of words.
If there's, can I ask a quick question?
Yes.
If there's an ambiguity in how the different macroscopic states are defined, are you still going to end up with the same answers in the end? Like, is there an invariance somehow on how things are defined? You're always going to end up with the same answers.
There is, if there is a microbe, and for example, in the end, we live in particular world, and by definition, we are local entities, local objects. And this theory of universal wave functions, suppose it's explained why we always agree about everything. If we perform experiment and we meet, we will always agree about results.
Okay, so
we can speculate about parallel worlds, what is there, but there is no any there is maybe one more thing. In fact, I'm kind of parasite on textbook quantum mechanics, because in textbook quantum mechanics, we say that if we perform a quantum experiment and the pointer has different position, then one of them, we collapse to one of them. And so we collapse to one of those wave function. And the wave function of the word is this collapsed wave function of the standard interpretation. In standard interpretation, we all agree. But the difficulty which I see, why I don't want to believe it, the collapse. There is no any good theory for collapse. It's non-local and it's random. But apart from that, we cannot explain collapse. Given that there is a collapse, what we see around is completely consistent. And the only thing I say, okay, the collapse is only for me, because this is, I call what my world, and this is where I live. And because I cannot see interference macroscopic objects, I don't have to worry about parallel worlds which exist, which others say they don't exist, so they don't worry about them. I say I don't worry because it's not feasible to see that they interfere with my world. Okay.
Okay.
No, we'll see. Maybe I'll. Okay. inside the world, there is illusion of randomness and action at a distance. Because inside the world, our experience is like experience of everyone who believes in collapse. It's the same thing. Everyone who believes in collapse, believes in Bell inequalities, and believes in that if there is a particle in two locations in superposition, like Einstein boxes, I measure in one of them and disappear in another. But I say no. It's in my world it will disappear. For me, it disappeared. But there is a parallel world in which I didn't find it. It's really in the other place. Okay. So, in fact, this is more important. So if you want to clarify, I'm ready to discuss it. Then there is this probability. The probability is difficult to understand in many words. And this so people will less believe in many words in trying to think about probability. Because I believe I found satisfactory solution, but I agree that it's very difficult to think about probability in many, more difficult to think in probability in many words than in most other interpretations. Okay, I will continue. So the meaning of probability. First, I say there is no meaning. Really, I want to say everything deterministic, so probability, strictly speaking, doesn't exist. But again, we perform quantum experiment, we have to kind of introduce how to deal with it, how to consider it. But at least I say the following. If I'm going to perform quantum experiment and somebody asked me before, what is the probability that I will get result A, or I will be in word A? I say there is no meaning for it, because I know that the observer or I will have two descendants. One will see A, another will see B. So how I can say what the probability which I understand, it should happen to A or B, but both A and B happen. So one cannot ask what's the probability of the result of quantum experiment, at least before the experiment. Maybe one can say after the experiment it happened, so there is particular result. But I say no, there is nothing interesting, because after the experiment, if I'm in the word B, the probability of A is 0, not of interest. Even in the beginning, I had this quantum state alpha A plus beta B, but in the end, I was in the word B. So in word B, I know there's no probability for getting A. And now, sometimes people say the following. Let's put impenetrable wall and perform experiment, but I'm outside and I don't know what happened. So I run the experiment and the word split to two words, A and B. And then what is the probability that I'm in the word A? And I say this question is as meaningless as one for future, because this observer now in two words. For him, there is one universe, there are two worlds, but he is in both. The situation when one can talk about probability is the following. There is this wall, but then, and the student behind the wall performs the experiment. And then he sees the result and comes to my room. Before he tells me the result, he asks me, what is the probability for A for B? And let's say that I knew that the coefficients alpha and beta, so I know the quantum prescription. Now, I say I have a probability. Do I say I have probability? Because when my student see A or see B, it's slight difference for him. He will enter the rooms in slightly different moment. He will look slightly different. So when I look at him, I will split because I will see two different results. I still don't know if it's A or B, but there are two of me. There is A and there is B. So now there is a matter of fact for each of me, if I'm in A or I'm in B. Now there is a meaning. Now I can ask. But this is really probability of self-location. I want to know in which word am I. I know that there is a word with A and word with B, but I, particular me, here, particularly, I will not see two of them. I will see I will split. He split before, then when he enters the room, I will split. And this probability of self-location, in which word am I? This is a probability which I can talk about.
What about in the case, can I ask a tangent
Yes.
question here? So what about in the case if there's a measurement that happens that's at a spatially separated location from where you're at? Like, does the story still play out the same?
Especially separated, it's equivalent to this. It's much better.
Yeah.
Somebody perform experiment on the moon, and then for 1 second, I know that the world split because he measured spin and get up and down. But for me on Earth, definitely for 1 second, I live in both worlds. And if the signal will not come to me, then it's still I live in two worlds.
So you still split.
I split only when something comes to me. If nothing comes to me, I do not split.
I see. Okay.
The word split. There are the number of words, how many? There is word A, word B. But I'm in both. There is a meaning that I can be in two words. In my words, both I'm both in word A and word B.
Right.
This is, again, I don't have to, we should not forget that Hugh Everett started all this, and he performs slightly different semantics. He has relative states and he has word for an observer, which I don't think it's okay semantics, but I prefer another semantics. There is no big conceptual difference. But if there are no observers, I cannot talk about words. And I want to talk about words in the beginning of the universe and much later. So in my semantics, in every word, all macroscopic objects are well localized. So if there is a Stanford experiment on the moon and it's performed, the pointer with our detector clicked, so it split. Even I didn't split. Even in my relative to my state, both things happened. Okay. Okay. So now in quantum mechanics and also in many words, in this situation, when this experiment was performed with alpha A and beta B, and I'm in this situation, I will bet, and I will consider probability of being in probability of self-location according to this measure of existence, which I call the alpha square or beta square. So I postulate it. Now, but especially in many word interpretation literature, there are many, many works, and also not in many works, how one can derive Born rule. And I also have one proof. I claim that I have to assume something. So what I assume symmetry, but symmetry, I don't think, it's not an assumption. It's kind of, I don't think it's special assumption. The real assumption is that no superluminal signaling. So I want to derive Born rule from relativistic causality and the fact that the space a priori symmetric, or at least I can consider it symmetric. So I consider a particle in symmetric which has symmetric state. It has 120 degrees symmetry rotation, and then to make it really symmetric, I will put identical observers near each one of them, and they will measure probability of finding a particle. This is one particle in the superposition in 3 places. So of course, only one of them will find in one word. I believe the word will split, but anyway, so now we're talking about standard, we don't talk about many words. Anyway, probability for each one of them to find a particle in any interpretation, to find the projection operator 1, there is a symmetry. But one have to be careful. I think in this situation, I cannot really use this symmetry because when everything is completely symmetric, if one observer found it or another observer found it, it's really the same situation. To be able to talk about probability, I need some labels. And in physics, we always have some labels. We say that there are some things which are not relevant for the experiment. So in all these three places, there are some labels which make a difference between these three places, but they are not, we find that they are not relevant to the experiment of finding the particle. Now we can say that the quantum state is symmetric, like A plus B plus C. And now from symmetry, we can say that the probability must be 1/3. The next stage, but this, okay, this is very special situation. We have this extremely symmetric case. Now relativistic causality allows me to consider it not necessarily so symmetric. Let's, one of the observers is really not as tall as others. But since he is far away, in this experiment, it cannot be that probability here will change, because he can just, he can sit down instead of stand, and now will change probability here, so he can send signals. So the probability to find in A, it's still 1/3, otherwise we can send signal. We can perform another experiment. We can put a beam splitter and put these two beams, put it together and make one state. So we can change our state from symmetric state to this state. But again, this is far away from here, and to prevent superluminal signaling, probability here should not change. So the probability here will not change. If we have this state to this state, the probability is the same. So from here, I can say that probability, if I have state like A plus B plus C and symmetric, and so if I have coefficient 1/√3, then probability to find the particle, it's 1/3. Now, let's say I have 1/√n. When 1/√n, one can say it's not so easy because the distance is small. How we'll do this? The relativity will not work immediately. But I can do it in steps. I have a symmetric state, and I have this, so I ask probability in A. It should be 1/n. Now, for a short time, when I start to move all these wave packets here, clearly, this and this, since the light still didn't come from here to here, it still will be a probability in A, it's 1/n. If this is 1/n, I can move again, and this is also 1/n, and then I can move again. In the end, I can reach this kind of state. So now I know every time I have coefficient 1/√n, probability is 1/n. Now, if I have not 1/n, but I have square root of m/n, I can do the following trick. I can consider this is my square root of m/n, and this is the rest I have from n plus 1 to n. They are, all of them, it's 1/√n. I know that each one of them 1/n. So since total probability is 1/n is 1, I know that probability of this one should be m/n. Now, I know that David Deutsch considers special consideration, but I think continual physics can tell me that I shouldn't worry about irrational numbers. And whatever I have coefficient, even it's not rational number, the probability is just alpha squared. Finally, this was about position. If I have spin variable instead of position, I can perform unitary swap between position measurement and sweep measurement. I do not expect that there will be difference. And so in every quantum state, then I really approve the probability to find. If I have a particular state with coefficient alpha, probability to find the state is alpha squared. Okay. So I have this, and the next question is, do I really again, I really strongly believe that to prove a Born rule, we need some assumption. I use relativistic causality. Many others use some other assumptions. I claim that without assumption, we cannot prove it. If I use standard quantum mechanics, it has unitary evolution until collapse. Unitary evolution obeys relativistic causality. But collapse doesn't obey any rules except that if it's probability, if amplitude 0, probability 0. Probability amplitude 1, probability 1. We can put whatever we want. For example, we can put the following kind of natural rule, which some people who attack many words frequently do. They say, let's say that if we have several situations, that every situation has equal probability, several macroscopically different situations, equal probability for all of them, independently on the amplitude, with one exception: the amplitude should be non-zero. If you have non-zero amplitude, then the probability of this event to find this result is 1 over n, when n is number of different situations. Now, this rule does not contradict anything. It doesn't contradict unitary evolution. Of course, it contradicts our empirical evidence. But the question, can we derive this rule without empirical evidence? Now, just to be sure that if I have this idea of relativistic causality, I can rule out this very simple. If I have experiment, I have a beam splitter, one go to A and one go to B. We have two words, two different situations, this click or this click. So probability to find click in B should be one half. Now, this is far away. I can put many beam splitters, and now this photon, instead of going here, it can also go to 9 detectors. If it go to 9 detectors, we'll have splitting to 10 words. So probability of this is 0.1. So if we do not allow superluminal signaling, then of course equal probability rule for all words is ruled out. Now, in many words, we don't have collapse. There is no additional rule. So this, I think, the reason why many saw that maybe in many words we don't need any other assumption, and maybe we can prove it. But first, again, the meaning of probability in many words is problematic. So let me briefly come back to the question how to understand meaning of probability. Before the experiment, there is no meaning because there will be 2 observers and they will get this. Also, I can consider these 2 observers if they'll move, depending if I'll move here or here. But again, I cannot talk about the meaning. What's the probability that I'm in word A when I know in which word there is no meaning. And also, if I'm isolated and I don't know about the outcome happened, I still say there is no meaning. I believe that clean meaning and very special meaning exist only in this special experiment, in which I ask to move me to different rooms while I'm asleep, depending on this result. And when these rooms are kind of identical, then in the end, I will be in a very special position. There will be a matter of fact in which word am I, here or here. Everyone else will have to say, oh, what's the probability of the me in A to be in A? This is, no, of course, 1, or B in B is 0. but I don't know in which word am I. So if they ask me, I have probability of self-location. My ignorance is not about the result of experiment. I know that both results happen. I don't know who am I. And then I will bet again, I will postulate the Born rule in many words. It's according to this amplitude square, which I call measure of existence of particular words. There are two words, this one and this word, and I think that I have different measure of existence. So I introduce this postulate of probability of self-location. It's a Born rule in many words. There is interesting situation with this in this kind of experiment. You remember Laplace said that if the world is deterministic, that and in an intellect knows everything, that such an intellect, for such an intellect, nothing would be uncertain. Not in this case. I might know everything. I know the wave function of the universe, but I don't know who am I. So self-location uncertainty, it might exist even if everything is known. So, and the claim is that I do need, in many words, it doesn't help me. I do need, in many words, the Born rule. Even the Born rule is this postulate about probability of self-location. Exactly because of the same reason, because I can introduce a game and say, oh, my self-location is, there are many different words and probability to be in every word. It's the 1/n of every word. And it will contradict nothing except my empirical evidence. So I cannot prove Born rule also in the framework of many words. Also in many words, we cannot derive the Born rule without assumptions. So it looks like I'm in time for summary. In my picture, the only ontology is this universal wave function. It's highly entangled. Maybe some people trying to think that if I present this picture, I have to show how I'll get emergence of classical words out of this universal wave function. And it's very difficult, but I think I don't need it. We do not know the universal wave function. We know only the wave function of one of our branches. And if we remember of experiments we performed, so we know about existence of some parallel branches. And sitting in one of the branch, we can understand what's going on. It's not difficult. There is no difficulty to see this, our word, when we see in our branch. I cannot understand when I perform quantum experiment and split, because either I believe in non-local random action at a distance collapse, or I say, okay, there is this parallel world, which anyway, I know why I don't see it. So to explain experience, we introduce the concept of a word, which helps is inside the word I can understand my experience. In the world, all macroscopic objects live in 3 dimensions, a product state. I need some postulate. The physics is this unitary evolution of this universal wave function. But then I have to connect it to my experience. One connection, if I have a wave function in the shape of a tiger, I say it's a tiger. I have also another connection for this probability case. If I have this, performed a special experiment, and I know that there is amplitude for one outcome and another outcome, but I don't know which one, then I should bet according to the amplitude square of particular outcome. And I think for Born rule, although it can be derived from making all kinds of assumptions, but if I use just formalism of quantum mechanics, use unitary evolution, this cannot be done. I have to introduce by hand, which is not, I don't think we should attack many words on these grounds, because in every interpretation, Born rule is placed by hand. Some people believe that in many words we can get it for free. I don't think it's true, but this is not a reason not to believe in many words. So thank you.
Thank you so much, Lev, for such a very interesting talk. Does anybody have any questions? I think I've got some. So one question I would ask you right off the bat is, from the perspective of many worlds, like if you're taking a measurement of something that is a continuous variable, is it really, how is that perceived? Like, are there, let's say you could divide space as finely as infinitely small if you want. Does that mean that you would have an infinite number of worlds that split off at any second, or how does that work?
I don't like algebra, and I don't like infinity.
Well, I don't like infinity either. I'm with you.
Because infinity has a lot of mathematical tricks which we don't see.
Sure.
And we never make, there is no, in the end of the day, probably there is everything discrete. You will have finite volume and final energy, everything discrete. When I have a screen and I get kind of blip on my screen, still it's made out of atoms. Yes, but even much before the atoms, the number of possible outcomes is always finite. So I don't have continuity. So, but yes, there are many worlds, and like people talk about Shenker cat, and usually say there are two cats. This is not true. There is one alive cat, and there are many dead cats, because he dead with radioactive decay. He dead in different moments of time. So we have many, but again, it's not infinite, because we cannot. If somebody will take me and move me 10 to the minus 100 centimeter to the right, my quantum state, I think, will not be orthogonal. Even I have many particles, it's still, there is overlap. So it's not, until I come to orthogonal state, we need, the number of orthogonal state is finite. So always finite, maybe big. And I don't know how big. This is difficult physical question. I don't know how.
Got it. Thank you. Okay, so we've got some questions here. I'm just going to unmute. People want to. Harris, go ahead.
Okay, thanks for the lecture. It was very informative and interesting. This might come across as a very silly question, and maybe even partially answered just by what you said now about measurement, but I'm going to ask it anyway. So is it true? So would you say that the first branching of our world occurred, or the only branchings of the worlds, or any world, occur when there's experiments going on or measurements, or how does that? That's why I'm saying, like, now you partly answered it, but so, like, would we say that before 1905 there was just one branch of our world, and the other worlds, like where there's no humans or no like big, no clever aliens doing experiments, they're just one branch? Because it seems to me like, okay, and I'll stop. I see you nodding, so I'll stop before I make it into a really silly question.
We performed quantum experiment by going to my word splitter in the link which goes to quantum experiment. And then I know that the word split. I have this situation when I have two outcomes. In this case, I'm sure that the word split. I'm pretty sure that in astrophysics, there are all kind of that some supernova explode in different times depending on some quantum effects, and there is superposition of a supernova explosion in different times, which signal come to us in different times. So it's also splitting the world, and so. When we perform quantum experiment, we know we split the world. I'm pretty sure they also split in different cases. We had fluorescent light about 20 years ago, and they were flicking, and this is clearly a quantum effect. So there were many splitting because of this fluorescent light. Now LED, I think they don't do this. So sometimes we can clearly, there is some splitting when we don't arrange a special experiment. It just it happens in nature. And it's very difficult question when exactly it happened. There is a paper which I cite in my encyclopedia on many words, that they say that if I'll take a coin from my pocket and put it, flip it, then because of some quantum effect in my finger, then even I get tail, there is a big weight of heads, parallel worlds. It's physics which I don't know, which I think it's of interest. I think it will be nicer that there will be not too many splittings, and the theory is kind of nicer, but it's not crucial.
Okay, so John has a question. I'm just going to unmute you here. Go ahead.
Thank you, and thank you for your talk. Are there measurable differences in the predictions of standard quantum mechanics and many worlds? Can we distinguish them eventually? Can we distinguish between these theories by doing the correct experiments?
Yeah.
So
I remember being Plaga submitted a paper about experiment, how to distinguish many worlds, the foundations of physics. And I was 3 times trying to reject this paper. It was published anyway. So then the question, the answer is not so simple. First, it's pretty clear that today there is no, again, in fact, so the one thing, there are these papers which claiming this, and I think they're incorrect. There are a couple of 2 more papers. There is a paper of David Deutsch, and also I am also have section how to test many worlds. And maybe the simplest test to describe is the following. I showed many times when I send a single photon to 2 photomultipliers. Now I have to spend $1 million and coherently reverse action of a photomultiplier, or make it come small photomultiplier, but big enough that some people will say, oh, it's macroscopic enough and the measurement happened. People who believe in collapse, they say that when a big enough device happened, then collapse happened. So it's feasible just to, I say it's never happened. So if I will spend a lot of money and I will make interference experiment with this, undo the quantum experiment, then it will tell me that there are no many worlds. I think every time today people make interference experiment with molecules which have like more than 1,000 atoms. For me, this makes me believe more and more that many worlds is true. Many worlds is true is standard quantum mechanics does not break down. And the collapse, everyone will say collapse. If I have a photomultiplier and it clicked, people say collapse happened. If I can reverse it, I can test it. But clearly today's technology doesn't allow this, and maybe later people will also say so. There are experiments today testing collapse theories, particular collapse theory, GRW, and maybe the Penrose. They have, but again, even then we will never, it will be very difficult to know because it's very difficult to distinguish between imperfection of an experiment or the real collapse mechanism. If we will have it very, very clean and we'll see collapse mechanism, we'll see, oh, there is a collapse, there's a particular collapse. But of course, collapse of standard quantum mechanics, this is, if we can undo the experiment, then we will see that collapse will not happen. When we send this in this 2 photomultiplier, the test is that the photon which comes back should go into the source. So if we'll put on another, there is a 2 input into the beam splitter. If we'll put it on the other input, a detector, and we'll undo the experiment many times, and we'll see that it always goes to the source. This is kind of a proof of many worlds, but it's not practical, as I said. Did I answer the question?
Okay, there you go. Okay, Francis? Go ahead, Francis.
Yes, thank you, Prof. Yes, I just wanted some clarity with the presentation you gave. You made mention of the shape that is the tiger, that if your wave is able to give you the shape of a tiger, you need not to have the real object. You just tiger, and you would have to decide whether to run away or not. My question is, I know for sound wave, we have to hear. For tidal waves, we have to look at the ocean. And for any form of wave, that when we take a smoke, for instance, when the smoke is part of the atmosphere, it could form some sort of structure or shape that we can observe. But that of the tiger that we spoke of, you spoke of and you used as an example, I'm quite confused. Do we see wave? And if we don't see wave, then I have no question. But if we can see wave, does it have a mass? I know sound can carry some mass, but does your wave, as in the tiger, the shape of the object, does it have a mass? And if it has a mass, don't we think that the wave or the wave that we observe in every physical phenomenon has to carry an object for it to be tangible? That is the question I have.
Clearly, if I see a cloud in the shape of a tiger, it's not a tiger. This shape of a tiger should continue to be for a while. It should be made out of the right particles. I explained interaction-free measurement. I didn't explain teleportation. There is some paradox. But in principle, not in practice, it will never happen. But in principle, one can imagine teleportation of me to the moon. When I'm teleported to the moon, the only thing teleported is my wave function. The electrons in the moon, it's the same electron like in Tel Aviv. So this is why I say that what's really making it me or tiger, its particular shape. Of course, it should be of the right degrees of freedom. It should be electrons, protons, made of atoms of material should be the same material. And then the wave. But again, the material itself, it's not a person. I'm not my electrons and protons. If I will be teleported to a moon, it's me. Even the electrons and protons are completely different.
Okay, thank you. Thank you.
Okay. Oh, there's some more questions coming. I was going to ask, do you ever, are you still there? Okay. So I think I read in your encyclopedia entry that that you can have worlds splitting, but you never have worlds recombining. Why does that need to be the case? It's
again, if I have super technology, or like people in all this field, people all talks about Wigner, who makes experiment on his friend, who can make an experiment on his friend at a superposition. If such a technology will be possible, then we can recombine the words. We can one word never influence the other. There is no interaction between them, but there might be interference. It's like in my first paper, which took me a long time, is a schizophrenic experience of a neutron and why we should believe in many words interpretation. And then I can trying to say that neutron has consciousness. When I put it 5 centimeters apart in neutron interferometer, I say it's 2 different words for him. But then I can neutron come to a crystal which he knows that usually it passes. But if I'm in, I have another in my experiment, I have another amplitude of the same neutron on the other side, I can prevent him to go through because I will make a destructive interference. So, but for neutron, we can do it in laboratory or for photons. But to make to recombine words, we need interference experiment with our words. We need interference experiments with humans, and this is, of course, it's That will never happen.
Yeah, I was hoping somehow there could just be like somehow like the memory gets erased or something like that, but I wasn't really thinking along the lines of interference. Okay, I think there's more questions, so I'll bring somebody else up here. So John has a question. Go ahead.
I think Giannis had his hand up first. Do you want to address that first?
His hand isn't up now, so he raises his hand again, then I'll.
Okay, so I'm wondering, Lev, if you can help me. I understand, the mathematical elegance of the many worlds theory, and that it's unitary, and what could be, what could be more mathematically satisfying than that? It's just a single theory of unitary evolution. I also understand that it maintains relativistic causality and locality, so it's very attractive from that point of view. But on the other hand, I have two problems with it. One is that it replaces one obscurity, which is the collapse of the wave function, with another, which is bifurcation, like when does splitting occur? So I'm not exactly sure I understand when splitting occurs. And the other is that it requires this huge Byzantine universe of this wave function that is just undescribably, incredibly complicated, as opposed to a single wave function. So can you help me out here? I'm trying to decide whether I should consider it more seriously.
About splitting, people say, when the splitting occur, tell me exactly when it happened, how many words are there? And for all this question, I say, I don't have good answer. And I don't need good answer, because this is not part of the concept of a word is my concept of conscious being to help me to explain my experience, given the ontology is a universal wave function. As an interpretation which consider this collapse as real event, they have to tell me when it's exactly happened, because it's something which part of the theory. I don't have it. It's up to you, and you can have coarse grain or fine grain. It in the end, David Wallace is very worried that you cannot say how exactly when it's happened and how many words exactly happened. I think in the moment I say that the words happen, exist with measure, then I don't worry. I can have many fine-grained words with small weight, or replace them by bigger word with a bigger weight. So I don't think it's. I don't have this. It's not a physical mathematical problem. I don't have to specify because it's my concept, and if my friend decides to have some another agreement about what macroscopic is, it will not make any kind of real difficulty. And about that Occam razor, that how many I have so many again, words are not ontological. It's like everyone will say it will be much more economical to put some big planetarium in a distance of I know 1,000 kilometers beyond Earth, and we don't need all these galaxies and stars and whatever. We can explain to put some lights there, and why do we need? I have my theory doesn't. It's much more economical. I don't have this collapse, which has very strange properties. First, it's not deterministic, and second, it has action at a distance. Even my theory is somewhat problematic. I have a non-separability. The words are non-local. And so this kind of, some people who work on many words trying to go for even more forward and trying to make everything separable, which I don't find the attempts very successful. It's too artificial. So, but for me, there is one universal. You say the one wave function is good. Yes, I have one wave function. It's highly entangled. Even this one wave function of collapsed one has to be highly entangled. Atom cannot be not entangled, otherwise it will not be stable.
Okay, John's got a question. Go ahead.
Oh, no, I'm sorry. I didn't put my hand
Oh,
in.
I
That
see.
was,
Okay, yeah, it's still up there. Okay,
thank you
fine.
very
Yeah, no problem. Okay, so Michael.
Yes. First off, I would like to know what is your opinion of the infinitesimal? And then I would also like to know, am I correct in thinking that you have a DeWittian interpretation of many worlds?
So first, if infinitesimal, I think I mentioned, when I mentioned that I don't like infinity, I don't have anything in infinitesimal. I believe then the physics is all these paradoxes with infinities, and in the end of the day, every time, the first time which somebody explained to me when I go to movie theater, I see in fact maybe in a good movie 24 pictures a second. I say, forget about continuity. I don't need it. I can explain much easier the world with finite and without continuum. And the second, you ask about DeWitt, yes? The DeWitt maybe played important role in many worlds because Everett was student of Wheeler, and Bohr said to Wheeler, no, 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 and everyone was silent until DeWitt was kind of pushed it forward. But on the other hand, I think he spoiled it. In DeWitt paper in this book on many word interpretation, his words are really separate. They're really separate. He doesn't talk about recombination. That Nichol asked me about why the words split, but they do not recombine. They do not recombine because of practical reasons, not because of conceptual reasons. And in DeWitt story, they cannot recombine, period. You just have many splitting words. And I think this is very bad theory. You have many words and you have kind of collapse to many words. So I very much don't like collapse. I think the DeWitt presentation is really bad presentation of many words.
Okay, Yanis has a question. I'm going to unmute you.
Thank you. I wanted to push a little bit back on the answer on teleportation and identity. It seems to be that you
The connection is not very good. And
Yeah, Yanis, the connection isn't good. We can't hear.
audible?
well, maybe you can write and then you can read and then
Yes, yeah,
maybe
good
I don't know, or do something with internet.
Or wait, yeah, the chat
Or
isn't.
maybe close the picture and then I'll hear you.
Hold on. Let me stop the video. I don't know, is it better? Is it better?
Yes.
Yes.
Is it? Yeah. Okay. I wanted to push a little bit on the idea of teleportation, and the way I understood it when you're answering Francis's question is that you don't teleport the matter. Teleport, you said the wave function, but it looks like the wave function is a product of my material. So yeah, but you do like reductionism. You say how is in
Yeah, the sound isn't coming through, Yanis.
The sound is very bad, but
Yeah.
if I have a few slides on teleportation, so they're supposed to answer. So maybe I don't know if there is no time limit, so I can go there if you want. Should I?
Go ahead. Yes, if you've got slides, please do.
Let me see. I'm sorry, didn't work this way. Yes. So do you see it? Yes.
Yes.
So this teleportation and matter cannot jump. This is what I said. It's science fiction, but quantum mechanics allows teleportation. How it allows teleportation? Because what's me? We do not have to move matter. All matter is the same. We need to move only the shape. And I believe that I'm just a wave function, as I said before. And and then we have a lot of particles here, and finally they move here. So before I was here, and then after this, after teleportation, I'm there. And the teleportation, if we talk about two-level system of spin-half particle, then we have this Alice, which is here, and it has this one part of entangled pair, and she can move. Somebody bring her a quantum particle, and she moves it to Bob, who is here. And what she do, she perform measurement with two outcomes, send 2 bits, and these 2 bits are here. And the reason why I mention it, what's paradoxical about this, this is very simple. So here there is explanation. This quantum state of EPR and my particle here can be rewritten in the other form. It's the same state, the same psi. And this other form, it's really this 4 what's called Bell states of particle, this particle and one particle of Alice's, and kind of rotated particle here. This is just kinematics of this quantum state. And if we move, rotate by pi in different z, y, or x direction, we get the same state. So the state moves from here to here. All what we have to do, we have to perform a quantum measurement here, send 2 bits, and get this. Or if I want to move me, then it should be a little more, but conceptually it's the same. I realize that if you use EPR state of Einstein-Podolsky-Rosen instead of singlet by EPR bomb, then we can do teleportation the same way like they proposed in the beginning. But the paradox is really for spin. We send 2 bits, and the spin to define which we need this big direction, which needs two angles essentially, 2 parameters, 2 continuous parameters, is moved to here. And the many-worlds picture says that before the procedure, we had this one particle of EPR, which was unpolarized electron. After the measurement, we have a mixture of all these 4 rotated, this particle or rotated version of it. But this mixture is equivalent to the same state. So nothing really changed. When performed this Bell measurement, nothing really changed on the Bob side. We have the same mixture. Unpolarized electron and polarized electron. What we do, we split the word, and the words are non-local. And when we know in which word we are, we can reconstruct our word. So Bell measurement changed nothing, but if we'll tell what is a word, then the physics universe, so there is this non-locality of our words. This is because it's really the mixture of all these words with all these 4 was there from the beginning. And the teleportation allowed us locally to split the word in such a way. So this is how I understand teleportation. This local operation splits this non-local words. Words are non-local if we have entanglement, and here we do have entanglement. And this is my explanation of teleportation. So maybe I stop sharing. I hope it helped. I don't know.
You probably covered what he was asking. Do we have any more questions? Well, I think this might be a good time to close things off. We had quite a good discussion. You had a lot of questions. So that's fantastic. So thank you so much, Lev, for such an interesting talk. It was, yeah, that was really interesting. I'm sure I'll be writing you some more questions afterwards.
And you're welcome. You see, I believe that it's very important that people will get consensus about interpretation. If somebody can kill many words, also, I don't know, I would not particularly like it, but again, it's better than to live uncertainty. So if everyone wants to discuss many words or other interpretation, you are welcome to write Zoom or whatever.
Very good. Thank you. Yeah, thank you so much. So I should mention that, I think this will be our last talk before taking a little bit of a break for the summer. But nonetheless, I hope to be organizing some more seminars throughout the coming year. So I hope to see everybody again. Thank you so much to everybody for showing up. Thank you, especially to Lev again for such an interesting talk. I really enjoyed it. And thank you to everybody for showing up, for your questions, and we hope to see you next time.
Thank you very much for hosting me. It was my pleasure. Thank you.
My pleasure.